So, what is a weak acid or base? By definition, as we talked about before, it's either the formation of protons and a weak base from a weak acid like this one here, formation of hydroxides and the conjugate weak acid as we have here, where you started off with 100% of the weak acid or base, and here's the key, at equilibrium, basically nothing has happened. Because it's weak, it means it doesn't make very many protons when you throw it in solution. It doesn't make many hydroxides when you throw it in solution. In other words, you throw a weak acid or base in solution, not a lot happens. And we understand this practically. If I throw some hydrochloric acid into water and I stick my hand down in it, I pull it out a few minutes later, there is no hand. I throw my hand down into some acetic acid, some vinegar, and I let it sit there for a while, and I pull it out, it's a little red. That's the difference between a strong acid, which chews your hand off, because I have nothing but protons in there, and a weak acid, which makes a few protons, which makes my hand a little red. Well, we are going to learn the math for what happens when we throw a weak acid or a weak base in solution, and they make a little bit of proton or a little bit of hydroxide. We can already imagine what this is going to mean on a pH scale. Instead of having pHs like for a strong acid like HCl, which are down here at a pH of 1 or a pH of 0, or for strong bases like sodium hydroxide, which are pHs of 13 or pHs of 14, we're going to end up getting answers for the pHs of weak acids and bases, which are pretty lame. They're going to be in this range, from around 4 to around 10 or so. They're going to be in a range where literally we can drink the water from these things and be just fine. Believe it or not, you can throw some weak acid into water, have a pH of 4 or 3, and drink it, and it doesn't bother you a bit. Say hello to soda. Say hello to a Pepsi or a Coke. pH 2 or 3 or 4, you drink it, big deal. I'll even let you drink Austin tap water, which, because it is sitting around limestone, which produces a weak base, will be up at pHs of 9 or 10, and you drink it every day right out of the tap. Doesn't bother you a bit. The chemistry that we're going to learn about with weak acids and bases is the chemistry of stuff not happening. And we're going to be calculating pHs that are lame, between 4 and 10, pHs that have no substantial impact on us. Now you might think, well then what's the point? What's the reason for doing this? But what we need to understand is that actually having a really good understanding of pH ranges can sometimes matter. It doesn't matter when we drink a pH 4 soda or a pH 10 tap water, because our stomachs are able to manage it. They have a way of dealing with and buffering against those pHs. But did you know that the pH of the human body is right around 7.2? And that for the human body to work well, it has to maintain that pH range within a couple tenths of a pH, or things go terribly awry. So while there are situations in which we can have several orders of magnitude of who cares, it's also the case that there are systems, like our human body, where understanding pH incredibly well will be vital to know what's going on. Which brings up this point. Every time you go to the medical schools and you say to them, can we pare back some of the freshman chemistry course, get rid of some of this stuff? All the chemists want to get rid of all this acid-base stuff, because to us it's kind of boring. But the medical schools, they say, no way you get rid of acids and bases. Acids and bases are the lifeblood, see that's a joke, lifeblood, blood, body, pH 7.2, of what we want kids to know about chemistry. They have to understand what makes and regulates a pH of 7.2. And the answer to that is the stuff we're going to talk about in the next several lectures involving weak acids and bases.